So now we're going to find the exact answer. I want you to follow along with me from the top. All right, stay right with me, and to help you know where I am, come on. I have my handy dandy, if it will move. Come on, there we go. Super duper pointy arrow. All right, so we are going to find the exact value. All right, so our equation is x squared. Maybe I should write that in somewhere. I have no idea where. Up over here. All right, really small. F of x equals x squared. All right, so that's our function. All right, so we are to find the exact answer, we're going to take the limit of Riemann's, oh, come on. The limit of, all I want to do is move it. The limit of Riemann sums. And we're going to take the limit of the right Riemann sum. Notice, so before we had L12, that was a left Riemann sum, 12 subintervals. R12 was a right Riemann sum, 12 subintervals. This is Rn because we have n subintervals. All right? So we're going to take the limit. And if we take the limit for the right Riemann sum as n goes to infinity, we can find the exact value. Now you can do this with a left Riemann sum or midpoint Riemann sum, although I think a midpoint Riemann sum would just be a nightmare in terms of difficulty. Let's use the right Riemann sum because I find it's the easiest. All right, so change in x is just like we always did, except now we have n subintervals. So our change in x is for n rectangles. So we have 6 minus 0 divided by n, or 6 over n. Here is the sigma formula, right, for the right Riemann sum. Right? So for the right Riemann sum, it's the change in x. We are summing up all of those rectangles. We're going to start after the first value, so that means we can use the first value that we're given. And then we have until n subintervals, right? And after we set this up, we'll take the limit because n is going to go to infinity. For the right Riemann sum, we're going to plug in our value plus the change in x. So as we're moving along, let's turn that into some values by plugging things in. This a here is your starting value. So the starting value, and actually let me write this as in integral notation. So I'm going to, because all the other ones will be. So I'm going to change that a little bit so we can tie that to our integral notation. So what we're really doing is this. So we'll have this notation and all the others. Let's use that notation here, even though we know what it was from the last page, but that was a video ago. All right, so we're starting with 0 and then plus our change in x because we're using a right Riemann sum. Now I put the equation as x squared way over here. If I didn't erase it, we'll just leave it there. No? Okay, we'll just get rid of it. All right, so we're going to plug in our values. This is the start plus the change in x times the number of intervals. All right, so that's what we're going to be evaluating. All right, so our starting value is 0 plus 6, we have our change in x, right, is 6 times n, and we have some number of intervals, right? So we're just going to use a variable. Don't use n because we've already used n over here, right? So this is going to be a new interval, a new variable, and we're always just going to use j, right? So because j equals 1 is our starting value, and n is where we're going to stop. All right. All this is, by the way, that's just the x value we're plugging in. What are we plugging it into? Our equation. As a little reminder, the equation, I'm going to actually put it back now that I erased it. There's only 2, by the way, that I have written up here in this video. The rest I will do completely with you. but I wanted to focus on one thing at a time. It's written so pretty, and it has all of the little the steps and words. All right, so now this is what we had up here, right? Our change in x times sigma. We're starting at j equals 1. We're starting after the first value. That's why we're plugging in a plus. And we stop when we get to the last value. So we have 0 plus 6jn. That's the value that we had over here. That's the value of x. And we're going to plug, hey, you come back. And we're going to plug that into the function, which is x squared. Right? So this is our value of x, right? And so we're squaring it, right? So if we square it, well, you square 0 and it's still 0. So here we have after we've squared, right? So all we did was we squared, and we have 6 divided by n times sigma, j equals 1, and we're stopping at n, times 6j divided by n squared. So we'll square everything. Square the 6, square the j, square the n. You can do that when it's a product and quotient. So now we have 6 divided by n times sigma, j equals 1. We're starting with the first rectangle, and we stop at n. Go to the end, right? And so here we just squared. It's all we did was we squared. 36j squared divided by n squared. You can factor out constants and changes in x. That can be factored out. We saw that when we did the summation formulas. You can factor that stuff out. It's not going to make any difference. And it was just like the rectangles, right, when we're doing the Riemann sums. I could multiply each rectangle by a half and then add them all together, or I can add them up and then multiply one time by a half. That's kind of what we're doing here. It's exactly what we're doing here. So rather than having to do it n times, let's just factor it out, and we'll do it at the end. So we're going to factor out the 36, and when we multiply that by the 6 that's already there, we have 216. We can factor out the n, because technically that's not a variable. That's technically a constant. It's our number of rectangles. Because it's not changing, it's a set number. That's why it's not a variable, right? That doesn't matter, it's a letter, right? It's not a variable because it's not changing. It corresponds with a set number. It's the j that's a variable. So we're going to factor out that n squared. So now we have n times n squared would give us n cubed. And we're summing up all the j squareds. Well, we have a formula for that. So we're using our power sum formula. This is the one for squareds. So we have our right Riemann sum, n subintervals. So once we simplify the summation, we're going to switch to the power sum formula. Once you switch to the power sum formula, there's no more summation in there, right? We have a formula to take care of that. So we have the 216 n cubed times, and this was just the formula from the other page, from the last video, n cubed divided by 3 plus n squared divided by 2 plus n divided by 6. That is replacing the j squared, right? Do switch the values back to the n's, all right? Don't keep the j's, because then, all right, won't be able to combine them. And the n and the j are essentially the same thing. All right, so we distribute the 260 n cubes to each of those terms. That gives us 216 n cubed divided by 3n cubed. Well, that reduces to 72. We have 216n squared divided by 2n cubed. That'll simplify to 108n. We have 216n divided by 6n cubed. That'll reduce to 36n squared. Now we take the limit, right? So we have to take the limit as n goes to infinity if we're finding the exact value, if you're using this formula. So we have the limit as n goes to infinity of 72 plus 108 divided by n plus 36 divided by n squared. And we know that if you have a constant divided by a power of n, as n goes to infinity, that goes to 0. right? You can think of it either as a horizontal asymptote if it were a rational function, or you can just think of it if you just have 108 and you have an ever increasing number, right? You keep dividing it by, you're going to have something extraordinarily small that's headed to 0. So our answer is 72 plus 0 is 72. So we took the limit as n goes to infinity, and that is the exact answer. That is the exact area under the curve is 72. So if you go back to the previous lesson's values, the trapezoid rule was pretty close. I mean, it was an overestimate, but not by much, 72.25. And then you can see these were less good estimates, right? But they were estimates, right? And if we wanted better estimates, we could put in more rectangles, or we could use a different rule. Midpoint or trapezoid will give us a little bit more accurate of a rule. If we use the midpoint rule, of course, that would have underestimated, right? Because midpoint underestimates on a graph that's concave up. But if you want the exact answer, then take the limit of the Riemann sums as n goes to infinity. And that's how we're going to find the exact answer. Now in the next one, I'm going to do another one. This one I left all up and I moved the little arrow around. This one I'm going to write. And I don't remember which ones are in your notes. So you follow along, you see it in the notes, you write it down. Right? I'm going to, I guess I'll leave it this. No, you know what? I'll just erase it. Then I don't have to worry about where I write things. Okay, I'll either take the limit at the bottom there. All right, here's our new function. All right, so we're finding the exact integral from 2x, that exact integral from 4 to 9 of 2x plus 3 dx. For the change in x, it's going to be the difference in the limits of integration divided by n subintervals. So n minus 4 divided by n, or 5 over n, is the change in x. All right, so now we're going to plug in the first value. So this is going to be the right Riemann sum. All right, so it's summing up, starting with our first value, so j equals 1. And we're stopping at n. So that's our endpoints, right? And we plug in. Now, the last time we plugged in 0 because that was the lower limit of integration. This time we're going to plug in 4. And then our change in x, so that would be 5j divided by n. Now we need to plug that into our function. So this is, right, this is x. And this is x after the first increase because it's a right. By the way, I'm going to do all rights. No reason to do the other ones. Just learn one well, and you can just always do a right. Actually, it's the most common one. I've never seen anyone do a midpoint, ever. All right, so now we need to plug that into our function, which is 2x plus 3. Right? So we have n equals the sum, j equals 1 to n, and we have 2 times 4 plus 5j over n plus 3. Oops, and I forgot to write one little thing in there. Don't forget our 5 over n. Once in a while I forget and I have to add it in at the end. I'm concentrating on the other part here. Now let's simplify that. So our next step is to simplify. All right, so our Riemann sum here. We have 5n. By the way, the capital N, the lowercase n, the same thing. My n's will bounce around. So we have 8 plus 10jn plus 3. We could simplify that a little further, right? 5 over n sigma, starting with j equals 1, the first increase, and we stop at n. So that would be 11 plus 10 over j n. All right, now let's split this Riemann sum. Or better, this is called a summation. Let's split the summation. Split and simplify summation. Yes, it's a Riemann sum, but let's focus on the fact that it's a summation. All right, so you get a 5 over n. And you get a 5 over n. Now, see, now it's lowercase, I told you. Now, we can factor out, you can't factor out the 11, it's not a coefficient, but you can factor out the coefficients on j, the only variable. All right, so, and then that j will switch to our variable, which is the n. In this case, though, until we switch to the power sum rule, right, our variable is the j only. So we have 5n sigma, nothing we can do here, j equals 1 and 11 plus, this would now be 50 over n squared, sigma, starting at j equals 1, ending at n, and just the j is left. So now, I wrote too big, let's go to our power sum rule. Actually, I'm going to move this, we'll take the limit. I'm going to just go down the line here, and then I'll go to the other column. All right, so now it's power sum rule time. Yay. All right, so now we're going to have 5n times 11n plus 50 over n squared times n squared over 2 plus n over 2. All right, and now we'll distribute that. So that would be, so the n's are going to cancel, right? So this is 55. Right, and then here again the n's will cancel. That'll be 25. And then we have 25 over n. We're running out of space here. Just move that over. Now we can combine the 25 and the 55. We should, right? Just numbers. Right? So we have now, so we're going to take the limit. So now we're going to bop over here, because I have no more space unless I expand the board. We're going to take the limit of the Riemann sum as n goes to infinity. So that would be the limit as n goes to infinity of 80 plus 25, that's a weird looking plus, over n. Of course, we know that the limit of a constant is just that constant, no matter what n is going to. And the limit of any constant over n as n goes to infinity is going to be 0. So this is 80 plus 0. 80 is the exact area under the curve. And we have done it. So you see limits come up in everything. Right? They've come up, they were the definition of the derivative. They are now the definition of finding the exact area under the curve. So limits are everywhere. Right? And that's our steps. Now it may seem tricky at first, but just the steps are the same like every single time. The only little variation is, of course, what numbers I'm plugging in and how I'm simplifying it. You know, this was 2x plus 3. if this had been, 4x squared, I would have squared, then multiplied by 4, right? So the only thing that changes is how we simplify it, depending on what the equation was, what number I plug in, depending on what the lower limit of integration is. The change in x will change depending on what the difference in those x terms are. And which of the 4 rules I use will change. If I have a square, or do I have just a x to the first power, or a constant, or x cubed. But that's it, really. Other than that, it's the same steps over and over again. And with practice, you get good. And you can always just refer to another problem to help yourself out. So definition of the definite integral: if f is defined on the closed interval a, b, and the limit of Riemann sums over our partitions of x, so the limit and so it has that change in x there going to 0. So the change in x going to 0 is the same as n going to infinity. So if the change in x goes to 0, right, if the width of the rectangle goes to 0, we can fit an infinite number of rectangles in there. It's said to be integral on AB, and the limit is denoted as, so the limit as the change in x goes to 0, which is the same as n going to infinity, is the definite integral from a to b. So now we're not approximating using Riemann sums. We are finding the exact answer using the limit of Riemann sums, just like we found derivatives using the definition of the derivative, which was the limit of the difference equation as n goes to 0, as h goes to 0, excuse me. Right, so functions are continuous. So the right-hand Riemann sum is the same as the left-hand Riemann sum. It's the same as the midpoint Riemann sum. When we're talking about taking the limit as n goes to infinity. So whether I take the limit as n goes to infinity of the right Riemann sum, or the limit of the left Riemann sum as n goes to infinity, or the limit of the midpoint Riemann sum as n goes to infinity, we get the same answer. I find the right Riemann sum, taking the limit of the right Riemann sum, easier, and that's the only one I'll be using. I don't even want to venture to say what the limit of the midpoint Riemann sum would look like. There'd be no reason. All right, so here's our next one. All right, so first thing, try to write smaller. Change in x. That's our first step. All right, so that's just 7 minus 2. Well, I must like that number, this number here, divided by n subintervals. So, well, again, it's 5 over n. That's all right. Must be my favorite number. All right, I'll try to change colors each time. All right, now we want to find our first value. First x value. All right, so that would be, we have the f of 2. Right, and then, oops, don't close your parentheses, plus the change in x, right, because we're using a right Riemann sum there. I can talk at the same time. Right, so our first value is f of 2 plus 5 over nj. Right, so 2 is the starting value right here, right? And we're adding a change in x because it's a right Riemann sum. All right, so now you substitute that into the equation. And I may not write the steps each time. I'll write the work, but maybe not in words. Come on, because then I'm waiting. Substitute into equation. All right, so then that would be 3 times 2 plus 5 over nj plus 1. Right? That matches our equation there. Right? So this is the 2 plus 5 over nj. That's our x value. All right, so now we'll simplify that. So 6 plus 15j over n plus 1. So that's going to be 7 plus 15j over n plus 1. Now we're going to do a right Riemann sum. And I'm going to come over here because I'm running out of space. Right? So our n equals, when we're summing up, starting with the first, oops, I was supposed to say j equals 1. Starting with our first value we plugged in, which is the first increase. That's why when we plugged in x, we didn't plug in a 2, we plugged in a 2 plus 5n over j. All right, so j equals 1, n, and so we have, oh, oops, I added the 6 and 1 together, but for some reason wanted to keep writing a 1. And we have, oh, and don't forget your change in x, so 5 over n goes outside the summation. And then we have the 7 plus 15j over n. Da-da-da. Now we're going to split the summation, or I could say split the sigma. It's even shorter. So we have 5, and everybody gets a change in x. We have 5n sigma j equals 1 to n, 7, plus 5 over n sigma j equals 1 n, 15j over n, right? And then we can factor out coefficients, and that does include the n, not the j. So this would be 5n sigma, there's nothing to factor out here. And then this would be 75 n squared sigma j equals 1 to n, and a j is left. All right, so now our next step is the power sum rules. Maybe it helps to write it like this, and you could see all the steps, even though it takes just a tad longer. I don't even know if it takes that much longer. All right, so this would change to, this would be 5n, and somewhere along the way I stopped writing the, just to remind ourselves, this is a Riemann sum. It's not horrible if you leave it off, but let's put it on there, unless it doesn't want to come on there. There we go. All right, but now we'll drop it once we switch to the power sum rules. So we have 5n times 7 plus 75 over n squared times, and then we use our rule, right, for the power sum. Oh, excuse me, 7n, and then the j will be, and we switch over to, remember, to the ends now at this point. That's going to be the n squared over 2 plus n over 2. Right, and we'll simplify it. So here the n's will cancel. This is 35. And then the second one, the n's will cancel. That'll be 75 halves. And then we would have 75 over 2n. Now we take the limit. I'm just going to take the limit. Right, so it'd be the limit as n goes to infinity of 35, let's combine those. So 75 halves is 37.5. I think, right? Yeah. So that would be 72.5. So we have 72.5 plus 75 over 2n. And of course, the limit of 72.5 as n goes to infinity is 72.5. It's a constant. And the limit of 75 over 2n as n goes to infinity is 0. So our exact answer here is 72.5. So now these are not approximations anymore. This is the exact area under the curve. If we did a left Riemann sum or a right Riemann sum or a midpoint or trapezoid, all of those would be approximations. But when we take the limit of those Riemann sums, then as n goes to infinity, then we have the exact answer. So there we go. All right, and so I hope breaking it down and putting all the little steps in there helps you out so you can see each little part. Right? And it's the same steps each time. Like I said, the only thing that can change is the equation can change, the change in x can change, and the power sum rules depends on what you have as your equation. And I'm actually going to erase the board. All my hard work. I'll leave the change in x up. Right. No. Hope it looks as nice. This is nice when I write it again. All right, so the change in x is up there. That would be our step 1. Our step 2. Let's find x values. All right, so we're starting with 1. Right? So it's going to be f of 1 plus 3 over nj. And watch how many different n's I use in the course of this. All right, there's our x value. Step number 3. All right, we're going to substitute into the function and simplify. Our function is 2x squared, so this is going to be 2 times 1 plus 3 over n j, all squared. All right, so we'll square first, and we'll multiply by 2. All right, so if I square it, I'll just kind of put it over here. Right, just so that we can kind of remember we're multiplying something by itself. Let me write that nicer. I can't even read that last number. I mean, I know what it is, but still. It would help if the letters would pop up while I was writing them. All right, there we go. All right, so now if we square that, right, we're going to have, our first would be 1 times 1. That's 1. And then the outer terms, right, they're going to be 2 of them, right? So instead of 3j over n, it's going to be 6j over n. And then we would have 9j squared n squared, right? And then we'd have to multiply that by 2. So that would be 2 plus 12j over n plus 18j squared over n squared. Okay, we got all our squareds in there. All right, so now I'm going to kind of switch over to the other side of the board. Why I don't work, why don't I do all of them on the right and then go to the left? I don't know. Maybe because there's some space over there, and then I'll switch over here and I'll just do the limit on the bottom there. All right, so step number 4, right? We need to, we want the limit of, we want to sum all of these up, right? Forgot the exact word I used. We'll use our summation rules, right? We're going to do the right Riemann sum. Right, so we have r of n equals, and then we change in x, which is 3 over n, sigma, j equals 1, and then we stop at n. And then our equation is 2 plus 12j over n plus 18j squared over n squared. Right, and then step 5, we're going to, and probably I should put parentheses. This all goes together. It didn't look as bad when it was 2 terms, but 3 terms, that's all part of that sigma. All right, come on, in green. Think it's going to show up, or should I write it again? We'll give it, we'll just do it again. How about now? There we go. Hopefully I won't see 2 of them. All right, so now we're going to split the sigma. Everybody gets their own little change in x, their own little sigma. So, oops, Rn equals. So you get a sigma, and you get a sigma. And you get a sigma. And just so it doesn't blend in too weirdly, just put a little box there. That was over. We started over there. All right, so now step 6 here, we're going to factor out coefficients. Right, so Rn equals, there's nothing to factor out here because 2 is not a coefficient. Here we can factor out the 12 and the n, so that's going to be 36 n squared sigma j equals 1 to n, and there's just a j. Right. So when I have the sigma, I need the j there, right? Because I'm saying I'm going to start with the first j. Right? But once we switch to the power sum rules, we're going to switch that j to the n. And then we can factor out, so that would be 54, right? And then n cubed. And then sigma j squared. So we have a few more power sum rules to use. All right, so step 7, power sum rule. So you see it's the same steps. Come on, I think this is my last one on this video. If we can finish. Power sum rules. All right, so we have then the 3, somehow we lost a 2 right here. Just forgot to write the 2 in. Come on. There we go. So we have 3n times 2n. And then we have 36n squared times, and these ones are easy. Oops, I meant to put a 2 there. It's easy to remember these 2 rules. See if I remember the square. N squared divided by 2 minus n divided by 2, or excuse me, plus. And then plus 54n cubed. And we haven't done any of the squared ones in a while, except for the one I had. So let's just remind ourselves the rule. Of course, we had it on this one. I'm just going to use that one. So, as a little reminder, right? So, don't worry if you don't remember the rules too well. Even for the AP test this year, you can use your notes. And otherwise, when if there's a time you need to memorize it, I noticed that the 3 times 2 equals 6, and so that can, and the 3 matches the cube, and the 2 matches the square. Right? So that's a way you can remember it. But if I put it in front of you. Okay, so this would be then n cubed divided by 3. That's what I meant to write. That's a 3. Plus n squared divided by 2 plus n divided by 6. So see how it kind of makes it easy to remember when you can see some kind of commonalities between the terms. All right, step number 8, and I think it's Green's turn to write. Trying to switch the colors up. Oh, actually, first I got to simplify it. Then we can take the limit, if I've got space. All right, so we're still on 7. Ignore that 8. So this would be 6, and the ends would cancel. And the first term, the n squareds would cancel. That would be 18. And then we would have 18 over n. That's just the 36 over n squared times the n over 2. And then we'll distribute again. All right, so 54 n over n cubed times n cubed over 3. The n cubes cancel, and that would be 18. And then we would have 27 in the numerator and n in the denominator. And then if we distribute to the last term, we're going to have 9 in the numerator and n squared in the denominator. And then the last step, I am going to have to, I'll expand the board just a tad. I'm going to erase that. Well, we saw what my answer was, so let's hope we get the same answer. All right, so it's the limit as n approaches infinity. So we have Rn is equal to the limit as n goes to infinity. So we've got 18 plus 18 plus 6, and that's going to be 42. And then we can combine the n terms. So that would be 45 over n plus n, 9 over n squared. And so when we take that limit, we know we're going to have 42 plus 0 plus 0. Right? We know that the limit as n goes to infinity of a constant over n is going to be 0. So 42 is the area under the curve. And I think I did have one more, but I'm going to end this video right here, and we'll pick up in the next video and we'll do another one. So I hope these are starting to click with you. All right, bye for now.